concentration, but how does this happen and why, and a few other things to clarify. So the molecules are, you'll often see a diagram like this, by the way. You'll often see like a cartoon sort of like diagram like this, with little dots representing molecules. Let's say these little pink dots here in the bottom diagram, let's say they're oxygen, because diffusion of oxygen is critical to get oxygen to all the cells in our body. So let's say we've got little oxygen particles here. Now, when you see a little diagram like this, and whether it's a animation or a static drawing, you'll often see represented that there are a lot of particles on one side and fewer particles on the other side, and that the particles are going to diffuse across the membrane from where there are a lot of them to where there are a few of them. Let's pretend we had 1,000 pink dots on the left and only 10 pink dots on the right, and so of course we're going to have a lot of movement of the particles from the left to the right till it's balanced out. But some important things to understand here is that we don't just have movement from left to right, and once they balance out, let's say we get to where there's 500 on the left and 500 on the right, it doesn't all just stop. These things never stop moving. So the molecules and the ions, they are constantly in motion, and they are constantly in random motion. So we don't just have traffic from where we have lots of them and then the traffic is headed over here to where there are few of them. What we actually have is the little molecules moving around in every single direction randomly. And it just so happens, looks like these are little boy molecules. No, that's just because of the symbol. Alright, so what happens is where you have more of them and they move around randomly, just by odds, just by random chance, because there are so many more of them, they're going to end up bouncing into each other, hitting each other, and then ricocheting off of each other. They have a bigger chance of doing that, and they also have a bigger chance of going over into the direction of the plasma membrane, and depending on the substance, whether it goes straight on through the phospholipid part or whether it's got to hit right into a protein channel, an integral protein, to make its way through. Either way, if there's 1,000 particles on the left and only 10 particles on the right, we have a much greater chance with the particles moving around randomly that the ones on the left are going to find their way to the right. However, and this is an important however, the molecules on both sides are moving around randomly, and some of the ones from the right can go to the left and some of the left can go to the right, and so this movement never stops. And so when they say they get balanced out, what it actually is net equilibrium, and so they're basically, roughly balanced out, but there's always going to be some still going from left to right and right to left, and they're always bouncing around. It's kind of like one of those air Lotto machines with the balls moving around, and if you had, let's say we built a little contraption with an air Lotto machine on two air Lotto machines next to each other, and a kind of a membrane or holes between the two of them. Let's see, we're stuck in a little loop here. Alright, there we go. Let's take a look at an air Lotto machine. Now this isn't exactly like the movement of molecules, because the movement of molecules is they are self-propelling, and with this air Lotto machine there's actually air blowing it, but it's kind of like this. And if the little molecules are bouncing around, and let's say we had 1,000 of them in this machine, they would just by odds, find their way to the little hole to find their way out faster than if we had a machine with, let's say, only 20 balls in it. And so they're not going to find their way out as often. All right. Now, if you think about that phospholipid bilayer. In the one video we saw, she talked about it like Oreo cookies with the creamy center. Or you could think about it like little balls with little tails. And of course we have a fluid mosaic model where, because of the chemical structure here and the polar and non-polar sides, these little phospholipids are going to self-arrange themselves, and when they get jostled about, they're going to go back into place. So in our little phospholipid balls with feet, the little balls are the charged or polar side, and because they're charged, they are hydrophilic, water-loving, and the little tails, the lipid sides, are hydrophobic or water-hating because they are not charged. So in that, the little lipid tails are our Oreo creamy center of the Oreo cookies. This center core, being non-charged, is hydrophobic. So it's going to kind of have a tendency to push polar molecules away and keep them from crossing over. Now, this is handy as part of a selectively permeable membrane, but it also poses a sort of a problem or a mystery of how do molecules then cross over this hydrophobic core. Well, think about what kind of molecules could maybe cross over and what other structure we have here in this phospholipid bilayer in addition to these phospholipids. Well, think back to the lab, the video with the bubbles. What let the pencil go through the bubbles without breaking or popping the bubble? Well, one of the methods is for substances that were lipid soluble. So if you take the pencil and you roll it around in the soap solution, or remember she talked about the kids putting their hands in the bubbles, and then once they're covered they can actually get their whole hand through the bubbles. Whee! So if it's covered in lipids, it's lipid soluble, then those substances can go right through. They can become basically like contiguous or become one with the bubble solution and make their way through. Little particles, little molecules, little ions, some of them are small enough to pass right through the phospholipid area or through the membrane channels, such as oxygen and carbon dioxide, and sometimes they are assisted by carrier molecules that specifically link like a lock and key to specific molecules. And we'll take a closer look at how that works specifically. But think about some of the processes that you know about, maybe in the video, a critical process that we have to do all day long that requires diffusion happening at a rather rapid rate. Well, let's think about breathing. So we have to get oxygen into every cell of our bodies. How does this happen so quickly? Well, because, these are just molecules bouncing around. And every cell in your body needs to get oxygen. Well, fortunately, the plasma membrane is very, very thin. In fact, it's only about as 1/1000th the thickness of a piece of paper. So the distance that they have to travel is very short. And this is critical for getting oxygen into the cells. And one of my favorite anatomy podcast lecturers, I learned something really fascinating from him. His name is Dr. Gerald Cizadlo, and he's kind of got like this Garrison Keillor kind of voice, and just brilliant at explaining the physiology. You can look him up and listen to his anatomy and physiology podcast. But Anyway, one thing fascinating I learned from him is how close every cell in the body has to be to the capillaries to get oxygen, or they'll die. How close do you think cells have to be to capillaries? Think about the blood vessels bringing blood from your heart out to the cells, and those little blood vessels get smaller and smaller and smaller and smaller until they're these rich capillary beds. Well, those capillaries have to be within 2 cells distance of each and every cell to keep it alive. So if you picture that with how many cells we have in the body, I mean, that is a very, very, very vast network of capillaries. Pretty incredible. So let's take a look at how this diffusion happens specifically. Now, each of those mechanisms we just mentioned basically has, a specific name. So when the substances are small enough to just travel right on through the without any help whatsoever, they can basically do that through the phospholipid portion of the membrane. This picture on the far left, the little teeny tiny molecules, like oxygen, can go straight on through the phospholipids, and that is called simple diffusion. So when the little teeny ions and molecules can go straight on through the phospholipid bilayer, that's called simple diffusion. Now, bigger molecules, for example, they're going to go through protein channels. There's actually different kinds of integral proteins, but if it's a kind of a protein channel where different substances can go through and it's a non-specific transporter, it's basically like a water slide. In fact, they call it an aqueous channel. So these can be called non-specific transporters, but the common term that rather than talking about non-specific transporter versus specific transporter, what the most common thing to look at or to call this here is facilitated diffusion. And that would be our second picture here. So if a substance can go through an integral protein, go through the little water slide, then that is using basically a non-specific protein channel. And these diagrams, and this is a very typical way to show this kind of a cartoon-like drawing of these integral proteins. But one thing I think is really cool about proteins, and is actually going to be important to understand a lot of physiological processes, is that proteins are really, really huge molecules. They have lots and lots of amino acids strung together. It's not uncommon to have hundreds of amino acids strung together in one protein. And so what happens with a super long string of amino acids is you're going to have parts of this really long chain that have slightly positive, slightly negative charge. They're going to basically then attract other parts of the chain, and so what ends up happening is it gets all folded in on itself, and it becomes like this very intricate, complicated origami structure. And so rather than this kind of simple, straight tube, if we looked at an aqueous channel or a water slide, it would be much more like one of those really fun twisting tube kind of water slides. And that may seem like, kind of a detail that doesn't matter at this point. It's certainly not something I would test you on, but these kind of concepts become important to form pictures in your head and to understand physiology as we go along and understand different processes. Because trust me, if you don't understand that proteins are really giant molecules and that water gets attracted to it, these different things I'm going to explain along the way, I mean, we're really laying some critical groundwork concepts here, then as you study each system of the body, there's just going to be a lot of memorization. And anatomy can seem really boring and just like a lot of Latin and Greek terminology if you're just memorizing stuff. But once you can start to understand the concepts and form a picture in your head, it becomes completely fascinating. And then when you start to think about processes like this going on in every cell of the body, and that all these cells are interacting in tissues, and all these tissues are interacting in systems, and all the systems are interacting, it's pretty incredible. Now, there's other integral proteins where the substances that go through basically have to fit like a specific key that fits a specific lock. Kind of try to draw an old school kind of a key here. My grandma actually had like these kind of cool, I actually have one of them, one of these cool old kind of keys. And now the actual shape here actually again comes to that complicated, twisted origami of the really long protein molecule. So what we have here is a lock and key kind of a mechanism where this twisted little fold of the protein that's going to have amino acid has to fit chemically perfectly with this little slot, or it's not going to open up the channel. So just the right, let's say it could be a protein, it could even be a, here in this example they're using a glucose, in other words a sugar, and let's say it fits just right, then it can go through the carrier molecule. But facilitated diffusion, whether it involves specific channels or non-specific channels, works with integral proteins embedded in the phospholipid bilayer. And it's basically like, substances that are too big or they're charged wrong to go through without some assistance or a special, bigger way to get through. And it's like taking a shawl and wrapping the molecule to carry it across. Or if you're taking a walk with your kids or your dog and you come across some shattered glass on the sidewalk and you want to safely get them across that glass, you could pick them up and take them across. Now our last example of diffusion is osmosis. And osmosis involves the movement of water across the barrier. And water is pretty tricky here, that it can actually move through the phospholipid part or special embedded proteins called aquaporins. Stuck in a little loop here again, excuse me. I would press pause here, but if I do, it's going to throw off the timing of the voice and all of our annotations. So pardon me when we get stuck here. There we go. Sorry about that. All right, so how quickly substances diffuse across the membrane actually has different variables. And the speed of diffusion is very important. So it's important to get substances like oxygen to the cells quickly and constantly. And we have a lot of substances that we have to get in and out of the cells. So the body has to actually basically strategize or maximize its ability to get diffusion to happen quickly. In the little video that we just watched, they talked about the higher the concentration gradient, the quicker the rate of diffusion. And that is true. So if there is a bigger difference of the number of molecules or the percentage of molecules, a bigger concentration gradient, then the diffusion is going to happen faster. There are other variables as well. If it is a higher temperature or warmer, the diffusion is going to happen faster. And that's actually why I have the pictures of the bee boxes here, other than the fact that I just completely love bees. A video or two ago, I gave the analogy and talked about how if you have some bee boxes in the sunshine and some bee boxes in the shade, when the sun warms up the bee boxes, you'll see a flurry of activity where the worker bees come out of the little slits here at the bottom. If these boxes on the right are in the sunshine, there's going to be a lot of bees, just constant traffic in and out of these little slits when they're warmed up. The little worker bees are going to come in and out, do their little waggle dance, show their friends where to find flowers, how far away it is, where the good stuff is. But over here, these boxes on the left, if they're in the shade, you're not going to see much activity. It's going to be pretty sleepy hives there. This is a good analogy for diffusion, how it happens faster with higher temperatures. But there's other really important ways to change the rate of diffusion. And one of my favorite things to look at is how surface area influences this, because the body has to maximize increased surface area for all kinds of different physiological mechanisms to happen effectively in a timely manner in every system of the body. And not just diffusion, but all kinds of examples. So far we've looked at the diffusion of oxygen, to take oxygen into little alveoli in our lungs when we take a breath in, and then when we actually get that oxygen delivered out to the cells in the body, we need to increase the surface area. The body increases surface area for other things as well, not even just diffusion, but like the brain, how the brain is structured. So let's draw a little diagram, and in case you can't just quite already picture this, let's take like a straight line. Let's pretend this line was straight, first of all. Let's pretend this line was straight. Let's pretend this line was 10 centimeters. It's kind of hard to draw with these computer pencils. Let's pretend this line is 10 centimeters, and let's pretend it's a semi-permeable membrane, and that we have lots of molecules bouncing around here on the left, and of course they're bouncing around, moving about randomly in every which way, every direction. Now, in our little 10 centimeter line, this is basically how much room we have, or opportunity, for these molecules to randomly bounce into this membrane and cross over. Well, think about it. If you wanted to increase the speed of diffusion by increasing the surface area, and we basically had a limited space in this regard, we basically had from point A to point B to work with, what could you do to increase this surface area? I'm going to use a different color here for my surface area increase solution. You could basically make little valleys and mountaintops, little innies and outies, take the same distance between A and B, take a little roller coaster ride up and down, in and out, and the cell membrane does this all of the time. It's a brilliant strategy with cilia and microvilli and villi to make little ups and downs, hills and valleys. And now we've taken this 10 centimeters, and obviously I can't really measure what I just did, but I'm just going to guess here. If we actually took that same distance and measured it, I'm going to say maybe we made it about 10 times or more of what it used to be, of all these little spots where the little molecules could have an opportunity, have a chance to bump in and then cross over. So now there's all these little different spots, every single one of these little tiny spots where things might bump in and cross over. And the body takes advantage of this to fit stuff into small spaces too. So not just for diffusion, like we want to get particles, molecules, and ions across, like, but we could do it for, just to increase how much space we could fit in too. Like the brain. The brain doesn't look like a basketball. It looks more like a cauliflower, so that we have these little ins and outs to increase the surface area. Alright, so that's pretty cool, and the body uses that strategy a lot. Even this concentration gradient. See, and there's so many cool concepts in physiology once you start to study them, once you start to understand them. But even this concentration gradient is brilliant. So if you think about it, the body, if it was just all passive, like a jellyfish floating around, let's say a jellyfish is floating around in the sea, floating around in the current, that jellyfish is going to get exposed to whatever it happens to float around. Let's say that jellyfish ends up in some currents where it's near ferry boats coming in and out all the time. It happens to be in